Can you see this pink? I picked it because it was a pretty color, but... Okay, so what I'm going to talk about today is infinite data structures. What does that mean? So let's start with a problem. You want to go from A to B. So you have a chessboard. You want to go from square A to square B. And you want to represent all the possible paths from A to B in a data structure. And you want to query that data structure for the first 20 paths, maybe the shortest paths, or etc. But you quickly see that there are an infinite amount of paths that stem from A, right? Because, I mean, all the possible moves, and extend that set, and extend that set, etc. How do you create a data structure that represents an infinite amount of paths, or stores infinity? What you'll need to store is not the moves themselves, but delayed computation. What does that mean? So, obviously you can't store the paths themselves. You'll need to somehow get the paths on the fly, right? Or as you go. So if I want 20 paths, I'll evaluate 20 paths. And this is really easy in languages like Haskell or some dialects of Lisp, because they have something called lazy evaluation. Lazy evaluation, you have a variable, you evaluate it when you want it, and not when the interpreter reads it. But who really wants to write in Haskell? No one wants to write in Haskell. Let's do it in JavaScript. So I think that it's pretty cool that we can do something like that in JavaScript. JavaScript is an eagerly evaluated language. It's not lazily evaluated. So we'll need a way to create a delayed computation in JavaScript. Now, if this sounds arcane till now, here, let me give you an example. Suppose you have x equal 3 times 2. If an interpreter reads it right now, it will put 6 in the variable x, and that's it. We can't build an infinite list out of something like that, because if you were to put an infinite amount of elements, it would be stuck in a loop. What you need to do is somehow suspend the evaluation of the next element in the list. To do something like that, you just wrap it in a lambda. You wrap it in an anonymous function. Can you see in the back? Okay, so x is no longer a variable here. X is a delayed computation. Only when you force x, only when you call x, will you get 3 times 2. X right now is just a dummy function. Do you see this? Okay. And what we say here is that we delay the computation 3 times 2. What you want, when you want to get the computation, you force the computation. This is all we need to build a stream. A stream is an infinite list. It holds an infinite amount of values. Let's build the infinite stream of ones. Can you see? I can't see it, so if you can't see... Right, so, okay. Ones is the function, is the anonymous function that when you force it, returns 1, and the recursive function ones. What does that mean? Right now, ones is a data structure that holds an infinite amount of ones. Okay? If we force the computation, what do you get? 1, and then a delayed computation of ones. You see that? Okay, thank you. Thank you. Okay, so 1 and a delayed computation of ones. And it won't evaluate to infinity, it will just stay there. If we take the second element and we force that, we also get this thing. If we create a function that will repeatedly force the call to ones, that means takes the second element, forces it, takes the second element, forces it, we get an infinite amount of ones, right? So let's call this take 20 ones. This will keep taking the second element and forcing them and concatenating them. Now that's really simple. You see, this is a stream. This is an infinite data structure. Let's build the stream of natural numbers. Am I going too fast? No, good. So this is a bit trickier because we can't put a 1 here, we have to put a variable. We use an auxiliary function called from that when you call it with an argument, it will return a stream. Here it returns the stream that starts with n and then calls itself recursively. So if we call it with 0, it will create a stream that starts with 0 and here call itself with the next element. And that's all you need to create the natural numbers. Do you see it? Okay. Now, you're thinking here it's all mathematical tricks, we're calling recursive functions, how is it really an infinite data structure? But I want to take a pause and say that these constructions in themselves are lists that hold in themselves the computation that will return the natural numbers. It's not some trick, it's a data structure that if we do functional composition on it, we call map, we call filter, we call drop, etc. It's something that we play around that holds the natural numbers. So this is exactly my point here. If we create map and filter, and I'll show you right now how do we create map, we will be basically dealing with a structure that holds infinite data. Here's how you write a map function. Who's written some functional style code? Just one or, okay, a few, great. Okay, so we take this stream and we want to manipulate it. Let's say we want the natural numbers, and now from it, we want to create the stream of multiples of 2. Okay? So how would you do this? Remember, we have an infinite list. So you can't call the multiple, you can't do every element times 2 because it's an infinite list. So you want to do it such that if we call map on the stream with a function that doubles every element, then we have to be able to create a new stream that every time we call a new element, it will double that element and put it in a stream. Okay, I'll give you the example here. Suppose we have the natural numbers. This is forcing the computation, right? So what happens is you get the first element. Sorry, the list that the first element of it. Yeah, so suppose it's the stream of natural numbers. When you force it, you get 2 elements, right? The first element, which is the element you had, like 1 and delay, remember? And the second element is that delay function, that delayed stream. Now we return a new stream where the first element is applied to f. F is our double function or triple function or whatever. Right here, so 1 becomes 2, 2 becomes 4, etc. And the second element of that new stream is calling map again recursively. Now, it does take a minute to figure it out, and I do encourage you to read it at home, but it's something that is very, very elegant because now we can write something like, we define nats really simply. Now map doubler to nats is now the stream of multiples of 2, and we take 20, we can take 100, we can, etc. We're operating on an infinite sequence, and it's in JavaScript, so that's funny. So that was all math. Why do you use streams in practical use? So remember A to B, that's a combinatorial problem that's pretty tough. Or how would you solve that in an elegant way? I wrote a library called Streams that does something like that. And I'll show you a demo right now. So here we have that same example. We put a start position, an end position. We put Simon, your lab. Okay. You put a number of solutions, and it instantly gave us the first 21 paths from A to B. And that was simple. This data structure here creates an infinite data structure that holds all the paths that stem from the starting position. What we do with end position, that goes in like a filter function where we can filter the path, we can filter, the stream with everything that ends with the end position. And then number of solutions is another functional composition that will allow us to take the first 20 solution. Now, it does sound a bit arcane, so I encourage you to go see that library, see how it's implemented, and I hope you learned something. Thank you. That's my talk.